do it right. You don't even trust your right answer. Come on, let's have a little confidence here. All right. Share. Okay, so here's what we have. Length and a width, and you want to maximize the area. We're going to use a side equation. We have 400 feet of fence. So in our picture, the fence goes all the way around the perimeter. So we need lengths of L plus L plus W plus W. So we have a side equation. It looks like 2W plus 2L is the 400. So I'll solve that for L. And divide by 2. So I get L is 200. Oops, got W over here. L is 200 minus W. So when I put that in for L, I get my area function. 200 minus W times W, which is 200W minus W squared. So that's what we want to take the derivative of. So we do that right here. I get 200 minus 2W. We set that equal to 0 to get the critical number. And we get 100 is W. And we verify that it gives us the max because the second derivative is negative, which means I got an upside down face and the critical numbers up here at the max. So there's the max. And the question wanted to know, find the dimensions. So if L is, if W is 100, and that's 100 feet, that leaves, that's 200. And so L is also 100. Okay. Did you get that one all the way through? next one. Next one. Next one. Go. Did I close that page? I'll just write it on board. How about that? The old fashioned way. We're going to make a box with no top and a square base. So draw your box in 3 dimensions where the base is a square and then it's got some other height. And it's not going to have a top on it. So, box, no top, and a square base. Has a volume of 500 cubic feet. Find the dimensions of the box that uses the least amount of material. Make a box here. Base is a square, so I just need one variable for the base. So let's say it's x by x. And then give a different variable for the height. And there's no top. How do you measure the amount of material used in this box? Area. So you've got 4 sides plus the bottom to be the total area. We want to minimize total area. And in this problem, the area is going to be 4 sides plus the bottom. So start by writing the 4 sides, the area of the 4 sides and the bottom in terms of the variables x and h. And you'll see that you've got one too many variables. So then you've got to use the capacity amount, 500 cubic feet, to write a side equation. Side equation is volume, your objective function is area. volume is product X times X. That's a time sign.
Yeah.
You should get them all in, and then you should get something to take the derivative of. The derivative is a function of X. I'm going to some name. Most of you are at this spot. It's a little area. There's 4. Each side has dimensions X times H. And the bottom has dimensions X times X. And so our side equation is going to be volume. $500. Volume is the product of the 3 dimensions. So X times H. So we're going to let H be 500 over X squared. And you're going to put that right here. And then take derivatives. Is that where you are? All right, let's make sure you take the derivative and see if you can find a critical number. Simplify it a little bit, take the derivative from there. You got an answer they want to check? Finished yet? Yep. Perfect. haven't taken the derivative. Oh, haven't. Yep. You should find the base is 10 by 10 and the height is 5. Anybody getting there? Oh, you're rocking on these. Look at that. Put your x's together. Right there is it over x squared on the right hand side. And then multiply those sides by x. Oh. All right, so I'll give the folks at home something to watch. I'll take the derivative here. Let's see, think of this as x to the negative 1. So I get negative 2,000 x to the negative 2, which is a negative 2,000 over x squared plus 2x. All right, we'll set that equal to 0. So if I've got a 0 on this side, I'm going to take the negative term and move it over. Let's move it over, so it becomes positive 2,000 over x squared is equal to 2x. Multiplied by x squared. And divide by 2. And the number that we raised to the third power to get 1,000 will be 10. We'll do a quick second derivative test. This again is times x to the negative 2. So a negative 2 times 2,000 is 4,000. X to the negative 3 plus the 2. And so when x is 10, I have my second derivative full of positive numbers added together. So that's positive. Right, so 2 positive i's make it happy. And so now our question was get the dimensions. So this is 10 feet by 10 feet, which gives us 100 square feet. To get the 500 square feet, this has to be 5 feet. Okay. So there's one on your web work where you're told something about the volume, and then you're asked to minimize the area. And then there's another one that says, here's the total surface area. What's the largest volume? So you just do it kind of backwards. Okay, this time we're going to inscribe a rectangle inside of a semicircle of radius 10. We're going to put the base of the rectangle on the diameter of the semicircle, and we want to know the biggest rectangle that can do this. Number 3. What is the length of the base of the rectangle with the largest area that can be inscribed in a semicircle of radius 10? We're going to put the base of the rectangle on the diameter of the semicircle so that it looks something like this. So here's the semicircle, it means half of a circle. And now I'm going to stick a rectangle in here. And I want to know the dimensions of the largest rectangle that could do this. To make it easier for you, let's put this on the XY plane. Like that. Well, this point here is at 0, 0. And this is a semicircle of radius 10. All right, so what's the equation of a circle of radius 10, centered at the origin?
X squared plus y squared is equal to m.
Yep. Thank you. Okay, so we need some dimensions of the rectangle. If this is on a grid, then I'm going to put this at the ordered pair x0, and nice and symmetric so that this is at the ordered pair minus x0. And that makes this at the ordered pair xy. So the length of this rectangle in terms of x is what? Two x that way, x that way. And the height of the rectangle is y. You want to find the largest area. So we want to maximize the area. And by the way, I've labeled it. What's the area of that rectangle as I've labeled it?
Ux
times y. I got one too many variables. But I have a relationship between the ordered pair x and y right here. So take this equation and let's all solve it for y in terms of x. When you do that, you put that y in here and have a square root in it, no problem. That's what we're going to take the derivative of. This says that y squared is 100 minus x squared. So it's the top half of the circle. I'll just take the positive square root. Tell me what y is. You're going to put that right here. Right? You can put that right there. So our area is 2x times the square root of 100 minus x squared is the thing that you're going to take derivatives of. So I hope you recognize you've got a product rule and a chain rule. So do your bestest and let's see what kind of critical number you get. Be scared if your critical number is not a pretty number. I have to write up square roots on it. I should make sure I can't see what you're doing. Just keep it well hidden. Keep going. You're on your way. Yes, you did get a pretty number or not? Did you get a good number yet? Positive exponents first. Really, you first should find it. One thing you can do to the other side, keep the sign, keep the positive. There. 100 divided by 4 is 20. You get next is 5, maybe? Anybody? No? I don't do math in my head. I will take the derivative. Not for each, I didn't think it would be. Take the derivative using the product rule. Camera over. A prime is the first times the derivative of the second. So bring the power down, raise that to 1 power less, multiply by the derivative of what's inside. And then the other way is copy down the second term. And take the derivative of the first. So I can take this half of that, x times negative 2x is negative 2x squared. I take the term with the negative power and I'm going to put it underneath with the positive power. And I've got this one here. So there's my derivative. I'm going to set it equal to 0. Try to solve for x. So I'm going to take this term that's negative and move it over and make it a positive. It's equal to this guy. Okay, so I'm gonna erase my words over here. From this step, I separated them so that I can take this denominator and multiply it up there. So that just leaves me a 2x squared on the left-hand side. When I multiply those two square roots together, I just lose the square root sign. So I have 2 times 100 minus 2x squared. Right? You with me? And so if I distribute, okay, move that over again. Okay, so I'm going to distribute the 2 in there. 2x squared is going to be 200 minus 2x squared. Get my 2x squareds together and give me 4x squared. And I'm going to divide both sides by 4. So 4 goes into 25 times, so that's 50. So x is the square root of 50. I can write that as 5 times the square root of 2 because 50 is 25 times 2. I think the second derivative is too messy, so we'll just believe that that one gives us the maximum area. And so our dimensions would be that we need this length to be twice x. So the length of our rectangle is 2 times that, so 10 square root of 2. And the height is, well, let's figure that out. We gotta find y, so here's x. Let's take the square root of 50, square it. So square root of 50 squared is just 50. So y squared is going to be 50, so y is going to be square root of 50. So 10 square root of 2 by 5 square root of 2 is the biggest rectangle that can go in there. Okay. So I think on your web work you've got something inscribed, maybe in a circle or a parabola or something like that. But you can use the equation of what it's inscribed in to get the y value. How close were you?
I got that answer, but I want to very extended.
But that's okay, because I saw what you're doing. You're writing it with common denominator. It's all great. It's fantastic. Okay, so now we're going to do a rectangle and fence again. So let me read this to you. The highway department is planning to build a rectangular picnic area for motorists along the highway. It's to have 7,200 square yards, and it's going to be fenced off on the 3 sides not adjacent to the highway. What's the least amount of fencing to go around the 3 sides but still enclose the 7,200 yards, square yards? So let me try to write that. Okay, so we've got a rectangular picnic area. It is to have 7,200 square yards. And it's fenced off on 3 sides, not adjacent to the highway. And what is the least amount of fencing for this job? So here's the picnic area. It's open on this end so they can get in there. Right, they all park the cars here. bad question?
No, it was
That's-
interesting. She said, what is the circumference of the square? I said, perimeter.
Couldn't think of
She was like, yes.
Okay, all right, so this is square yards, so this is gonna go with our side equation. That's an area for the side equation. Sticky some variables here, and the fencing just goes here, plus here, plus here. Okay. So I'll use X's and Y's. Up and down is a Y and horizontal is an X. So the area is independent of whether there's a fence there or not. The area is X times Y, right? That goes with the side equation. And then the fencing is what you want to find the least amount of. You want to minimize X plus 2Y. Let's call it fencing is X plus 2Y. So you got too many variables in your objective function. Write the side equation, put it in there, and see if you can get you some critical numbers.
Would we just say this to be last, whenever we're trying to find this, or would this be put into the area? Just because like. Oh, wait.
Area doesn't matter how much fencing you have, just X, Y, and Z. Okay. Then solve for one of your variables. Oops. And stick that into your objective function. Okay, that's area, that's square yards. So we're at an equation, that's not area, that's fencing. Right? Fencing you add, area you multiply. X, Y is equal to 7,200. Solve for either X or Y, and then go back to your fencing equation. Right? Here's your fence. The area doesn't, so the X times Y is 72. Okay? No, because that's not an equation, that's a function. Here's what you know that it is. That's the equation, X, Y is 72. Right? Area Remember? Yeah, pretty good. Pretty good. Why is it? And the pencil is $240. Look at you. Good job. That is awesome. So your side equation is the area one, because that's square yards. Again, area doesn't matter whether there's fence there or not. It's just the product of the two dimensions. So I can, I don't know, which one did you guys do? Did you solve X or Y? Solve for Y? All right, so we'll put that in where the Y is. This is our objective function. That's why I stated it in words. So now my fencing is X plus 2 times 7,200 over X. 2 times 72 is 144. 2 zeros on it. That's what we're going to take the derivative of. That's x to the negative 1, so it's minus 14,400 times x to the negative 2, so that gives me an x squared here. And so we're going to set that equal to 0. I can put that over to the other side. And I'll cross multiply with the x squared up there. And then take the square root. Square root of 144 is 12. Square root of 100 is 10. So this is going to give me 120 as x. And then the question said, what's the least amount of fencing? So there's the x. X is 120. Put that in here to get the y. So y is going to be 60. So 60 plus 120 gives me 240 feet of fencing. Okay. So this one was kind of asked backwards of the first one. The first one you had the dollar or the linear amount for the fencing and you're asked to maximize area. This one you're given the area and you want the least amount of fencing. Okay, next one. We're going to make a cylindrical container with an open top. So draw a can with an open top. It's going to hold 1 cubic foot. So that's the volume, cubic units. Volume is 1 cubic foot. That's going to give you your side equation, right? Volume of a can is your side equation. If there's no waste in construction, find the dimensions require the least amount of material to make this can. Can with an open cup. When you're talking about a can, then the dimensions we need are the radius of the base and the height of the can. When we're done, we're going to have to give those numbers. And again, when we're talking about material, we're talking about surface area. And since it's open at the top, the material that's used is area. We need the area of the bottom. Added to the area of the material to make the sides. Bottom's a circle, so what's the formula for the area of a circle? That's not a circle. Pi r squared. Every one of you needs to get certified to teach geometry in high school, so that you remember these formulas. Okay, there's the bottom. Now, do you remember what the sides are going to look like when you cut that can open? A rectangle of height h. What's the length of your rectangle going to be? Circumference of the circle. Okay, let's take it to wild stab at what the circumference of the circle is. 2 pi r. Very good. That's h, that's 2 pi r. So that's what the sides look like. So the sides are rectangle, so you just multiply plus 2 pi rh. That's your objective function. You want the least amount of material. So you want to minimize that function, but it's got r and h in it. We don't want both of them. So see if you can write something with the volume as the side equation. You may know how to find the volume of the can.
1/3.
No, it's not pointed. Only pointy things have 1/3. Pi r squared times h. If it's a cone, then you have the 1/3. Okay, so use your side equation. How about you solve the side equation for h in terms of r? Plug that in what the h is, and then comes the tricky part. So you can get the blah, blah, blah critical number. I know you're not gonna get pretty over this time. You critical numbers with 2/5 or something like that? 1/5? Hebrew 1/5? So this is the thing you're going to take the derivative of once you get the h out of there. Write h in terms of r from your side equation. And then take the derivative of your area functions. Solve for h, you get 1/pi squared. And that's going to go here. The pi's will cancel. One of the r's will cancel. So this becomes 2/r. Right? That's what you're going to take the derivative of. You gotten that far? So what's the derivative?
2 pi r minus 2 r to the negative, or over r squared.
Alrighty, we'll make that jump. R to the -2 means it's the same as over r squared. So when I set this equal to 0, I'm going to move that over. So we have 2 pi r is equal to 2/r squared. So I'm going to multiply by r squared, and we get 2 pi r cubed is equal to 2. Now we'll divide by 2 pi. And that's where the 1/pi comes from. R cubed is equal to 1/pi. So r is 1/the cube root of pi. Because the cube root of 1 is 1. Right? Find the dimensions, so now we need h. Where do I get h? H is here. H is 1/pi times r squared. Like that. So cube root of pi squared. The cube root of pi is pi to the 1/3. And so when I square pi to the 1/3, I get pi to the 2/3. So down here is the same thing as saying 1/pi times 1/pi to the 2/3. Is that right?
Yes.
So these pi's will cancel, leave me a pi to the 1/3. Which is the same as that. radius is the same as the height for this particular can. Okay? So don't be afraid of goofy numbers. Okay, let's do one more. We're gonna look at a window that's the shape of a rectangle, but at the top of the window is a semicircle. So a rectangular window with a semicircle on top. All of that's made out of glass. Window has the shape of a rectangle. Surmounted by a semicircle. The entire perimeter of the window is 15 feet. What dimensions allow the maximum amount of light to enter? So do you want a big old fat window with a circle on top of it, or a skinny window? That's kind of the question. There's the rectangular part. There's the semicircle, the whole perimeter. 15 feet. The dimensions that allow the maximum light to enter would be area. Do you agree? The perimeter is 15 feet, and we want to maximize the area. So you see, you need to add together the two areas. The area of the rectangle plus the area of half of a circle. Maximize area is equal to the area of the rectangle plus the area of the semicircle. So write down the formula for the area of a rectangle. Don't care what variables you use. So I put an X here and a Y here. Then from here to here, this radius is going to be half of X. So if you can write your area strictly in terms of X and Y, and then we'll figure out what to do with that 15. So far I have this. The rectangle has area of x times y. I got a half of a circle, so I'm going to need a half the pi r squared. Right? And I said r was a half of x. So let's replace this r with a half of x. So when I square this half, I get 1/4. When I multiply it with that half, I get 1/8. So there's your area formula. It has two unknowns, x and y. We want to get the y out of there. This is our objective function. That's what we're going to take the derivative of. So we need a side equation that uses that parameter of 15 feet. Perimeter is length around on the outside. So the perimeter is this, plus this, plus this, plus this. So x plus y, half the circumference of the circle, plus another y. What was the circumference of the circle?
2 pi r.
2 pi r, so we only want half of that. So we want our circumference to be pi times r. R is a half x. So you can get your side equation going and maybe solve that side equation for y in terms of x. Over here, we'll write my perimeter. I've got x plus y plus pi times r, but r was 1/2 x, plus this y is equal to the 15. Okay, across the bottom, up, around, down. So I have x plus 2y plus 1/2 pi x is 15. So if I write y in terms of x, I'm going to subtract this, subtract that, divide by 2. Y is equal to 15 minus x minus 1/2 pi x divided by 2. Do that right? Yep. So that y is going to go over here, where this y is. So I have area is equal to x times that. There's x times y plus 1/8 pi x squared. So let's make this easier to take the derivative. I'm going to write those as 3 fractions, and I'm going to distribute the x. So I'm going to have 15 halves times x minus 1/2 x squared minus 1/4 pi x squared. And then I have plus 1/8 pi x squared. You go ahead and take the derivative from there. Put the pi x squared together, that didn't matter to me. Take the derivative from there, and I think you'll be okay. You're gonna get a funny looking critical number. Here's the derivative. 15 halves here, minus x. 2x times 1/4 is 1/2, so minus 1/2 pi x. 2 times 1/8 is 1/4, so I have 1/4 pi x. So I take a negative 1/2 pi x, add it to a 1/4 pi x, and get a negative 1/4 pi x. Trying to solve for x, so when we put a 0 over here, let's take both of these x's to the other side. So I have x minus 1/4 pi x, 15 halves. And I take them to the other side so I can factor out the x. X times 1 minus, we write that as pi over 4, is equal to 15 halves. So x, oh, it's plus, right? Thank you. And so x is 15 halves divided by that number. Okay, that looks kind of messy. Let's fix it. Let's make this 4/4. So I can write this as 4 plus pi over 4. Write it as a fraction so we can do a flip and multiply step. Cancel there, I get x is 30 divided by 4 plus pi. Again, that was too messy to check. But I think my second derivative is going to be negative, because that's a -1, that's a negative pi halves, that's a positive pi fourths. So it's a negative, so that means I do have a max. So that's x, and we want to know the dimensions. So gosh, then we have to go get y. That looks kind of messy. You just put that x right here. And there's r. So r is 1/2 of x. So 1/2 of that gives me 15 over 4 plus pi. And y is the messy one. Where's y? 15 minus x minus half pi x all divided by 2. And I've lost interest in simplifying. Did you follow all that? Yep. Did you get started on your whiteboard? Did you think of any that you wanted to ask about? You're saving those for Friday. All right, stand up and stretch for a minute. We're going to change gears here, and we'll go on to chapter 5.
I got like 2 hours of sleep last night, so my mind is
Oh, bless your heart. What are you doing staying up so late?
I work too much, and I'm taking classes right now, so the only time I can study is at like 2 in the morning.
What's your roommate loves that?
Oh, they all stay up.
God. our semester organized here. Good work, guys. Okay, so here's what's left. We've just finished chapter 4. We've done the part of calculus that involves differentiation. Now we're going to go back into the part of calculus that does anti-differentiation. At the beginning here, once we learned about limits and how we use a limit to take the secant line and make it into a tangent line, then we called that formula the derivative. And I gave you a function, and then you learned all the rules to find derivatives of a function. Now we're going to go backwards. I'm going to give you the derivative, and you're going to tell me the function. It's kind of like derivative Jeopardy. I give you the answer, you tell me what was the question. Now with derivatives, we learned the theory behind a derivative with the limit of a difference quotient. Then we learned the basic rules for finding a derivative. And then we learned the applications of the derivative. And somewhere in there, we learned the more complicated derivative rules, the chain rule for taking derivatives. So when we talk about anti-differentiation, we're going to look at just the basic idea, undifferentiate something. And we're going to learn some rules, basic rules. Then we're going to learn some theory of what this leads us to in terms of what can we use an integral for. And then we've got the more complicated integral that is related to the chain rule. I'm kind of debating on whether to do the more complicated one second instead of last, because that's the most important section out of chapter 5. And that's the one that you got to know frontwards and backwards when you're in calculus 2. And that's the one we always kind of rush through because we cover it at the end. So I might cover it second. I might have a good, but we're going to do section 5.1 for a little bit now. So we have 5 sections of chapter 5. In section 5.1, we just look at the basic idea of what an antiderivative is. So my questions will be here, and you're going to give you an answer. What function has as its derivative you guys are smart, so I'm going to give you the hard one right off the bat. 10x to the 9th. What did I just take the derivative of? X to the 9th. Oh, I told you were smart. So here's your answer, x to the 10th. All right. What function has as its derivative minus x to the minus 2?
1 over x.
It was 1 over x, right? Or x to the negative 1? Okay, what function has as its derivative x? X squared. Close. What's the derivative of x squared? Derivative of x squared is 2x.
No.
Okay. Are you going to take care of that too?
Oh, like any number, right?
Close. Right? It's going to have this in it. But when I bring that 2 down, I want it to cancel. So give me something to put right here before I 1/2. Right? 1/2 x squared. Now I'm going to ask you, is this the only thing whose derivative is 10x to the 9th? Give me another one. X to the 10th plus a number, right? Because the derivative number is going to be 0. So if I said, what function has as its derivative 0, you would have to tell me some number, right? Some constant. These things over here are called the antiderivatives of those things over there. So if I call these things little f, I'm going to do the antiderivatives with capital F. So when I define, an antiderivative of f of x is a function, capital F of x, where the derivative of capital F gives us little f. The process of finding an antiderivative can be called antidifferentiation. That's a long word. We're going to use some shorthand notation. When I asked you to find a derivative, I just put a little d by dx in front of the x to the 10th. And then that told you take the derivative and get 10x to the 9th. So that was my shorthand notation to tell you to take the derivative of that. My shorthand notation to tell you to take the antiderivative is I'm going to use this long, skinny looking s. That's called an integral sign. Then I'm going to put the function whose antiderivative I seek in here. And then I'm going to put this little fella right here. These two things are part of your instructions. It says find the integral of f of x with respect to x. Now you need this thing here because what if in my list of questions I asked what function has as its derivative 2? 2x, well, what if I'm taking the derivative with respect to t? Right? If I write this, then your answer is indeed 2x. But if I write this, I've changed the variable to a t. If I write this, then my variable's a z. Okay? So this part is just as important as that part. These two bookends tell you what you're integrating with respect to. And when you get into calculus 3, you're going to have a function of several variables in here. And you take times integrating with respect to each one. Now, when we tack on the arbitrary constant, then we have the most general antiderivative. Back up to here. There's my what function has that as its derivatives. There's this. Scoot over. All right, so what? So when I say said 10x to the 9th, then I would put this dx here, and you would tell me x to the 10 was what I took the derivative of, but I could also have had any constant hanging around on the end. And so when we had, what do we have here? Minus x to the minus 2. And you told me that was x to the minus 1 plus c. And then when we had x squared here, no, I didn't have x squared, I had x, didn't I? X, and you told me that was 1/2 x squared plus c. The c has some sort of meaning, because remember that when I take the derivative of something, I'm getting slopes. So if I know the slopes everywhere, well, if I look at parabolas, there are several parabolas. You can have them up and down and skinny, or a whole bunch of them. You just add a plus c, it moves them up and down. At a certain point, if they're all the same size of 1/2 x squared, they all have the same slope right there. So this number is going to tell us which one to pick. Should I pick when c is -1, which moves the parabola down 1? Should I pick when c is +1 or +2? So that plays a role later on. So let's get used to tacking it on. Okay, so let's play some more, but this time instead of writing it in sentence form, I'm going to write it with its little integral form. This is called the integral of x with respect to variable x. So that's how you read that whole sentence on the left-hand side. The integral of x with respect to x is 1/2 x squared plus c, because the derivative of 1/2 x squared plus c gives me x. So that's another cool thing. We can always check our answers. Whatever our answer is, if you take its derivative, we get back what we started with. So let's see if I write these things down here. What function has as its derivative cosine of x? What did I just take the derivative of to get cosine? I did. And then we want to tack on that constant there. That constant is sometimes called the constant of integration. All right, now this is a little bit tricky. What function did I take the derivative of to get sine of x? Good, good. Because derivative of cosine is negative sine, so the derivative of the negative cosine is the positive sine. What function did I take the derivative of to get secant squared of x? That's a tangent. What function did I take the derivative of to get the product of the secant of x with the tangent of x? What did I just take the derivative of to get secant tangent? Good. Okay, what function did I take the derivative of to get cosecant squared of x? Negative cotangent. Okay, how about, what did I take the derivative of to get a cosecant of x, cotangent of x? Negative cosecant. Negative cosecant. Are those all the trig ones that we had? Derivative of sine, derivative of cosine, derivative of tangent, secant, cotangent, cosecant. 1, 2, 3, 4, 5, 6. Those are our 6 trig functions. Okay. What did I take the derivative of to get e to the x? There you go. What function did I take the derivative of to get 1 over x? Good. With a picky point. 1 over x is defined for every x except 0. But I can't take the log of any non-zero x, can I? The logarithm is only defined for positive x's. So to make these two have the same definition, we put this in absolute value bars. Now let's work on a power rule. All right, so let's see. What function did I take the derivative of to get x to the first power?
1 half x squared.
That's right, 1/2 x squared plus a constant. We needed the 1/2 to cancel the 2 that we would get when we bring that 2 down. So what function has as its derivative x squared?
1/3 x.
There you go.
1/4 x.
And what about x to the 100? So if I wrote down a rule in general for any power other than -1, because when we have n is -1, then we have that rule. Tell me what we do. How is that power related to that power? Is n plus 1 over there? And then we've got to get rid of the n plus 1 that we would get when we brought it down here to take the derivative of. And then you tack on the plus c. So think how you take a derivative. Whatever the power was here before, you multiply first, then subtract. We're doing an antiderivative, so we do it in the opposite order. To undo the subtraction, we add. To undo the multiplying, we divide. So you add 1 to the power, divide by the new power. And if we have things in radical form, then we have to write them as fractions. For example, if I wanted to find the integral of the square root of x dx, I have to do what I did when I took a derivative. I'd have to start by writing that as x to the 1/2 power. Okay, then I don't have to think so hard because now I have a general rule. The power on the antiderivative has to be 1 more. So I make it 1 more. Then I'll do that addition, and then I put it down here. And then to show that I've got an antiderivative, I tack on the plus c. Now let's do the arithmetic. 1/2 plus 1. 3/2, so I have x to the 3/2 here, and a 1 over 3/2 there. But where I come from, 1 over 3/2 looks funny. What should I write instead? So we'll write that as 2/3 x to the 3/2 plus c. So just like when you took derivatives, start by trying to write everything as x to a power, then use your power rule. But then recognize if you've got your other transcendental functions, just think backwards. So we'll do a bunch of examples of this type next time. I'll show you what the plus c means for some application problems. We can do things like, if I told you what my acceleration was at an instant, then you can find my velocity and my position by going backwards, right? If I know position, I can find velocity and then acceleration. Now we're going to go backwards because now we know how. These are your basic antiderivative rules right here, and the x to the n power. Okay? All right, so we'll talk about your 4.6 web work on Friday. So if you guys give that a good old well shot, we can answer your questions on Friday. I think our test, our third test, will just go through chapter 4, unless you want me to put chapter 5 on it. But I'm going to keep covering stuff.
Do you have a class?
I do have one, but I've got 10 minutes. So if you want to talk about your schedule, we can. Let me stop the Zoom, so everybody on Zoom.